Earth's first billion years. The water in your body is old. Not old the way a piece of furniture is old, or the way a mountain is old, or even the way a civilization is old. Those things have lifespans that human beings can hold in their minds without difficulty. A piece of furniture lasts decades. A mountain lasts millions of years. A civilization, if it is lucky, lasts thousands. These are numbers that the human brain, given enough time and patience, can actually imagine. You can count up to 1,000,000 in your head, technically. You can picture 1,000 years as a stretch of human generations, grandparents and grandchildren and great-grandchildren, stretching back into a past you can almost reach. What we are talking about tonight is different. The hydrogen atoms in the water moving through your blood right now were forged inside a star that exploded before our sun existed. Before our sun was anything more than a slowly thickening region of density in a cloud of gas and dust drifting through a galaxy that had itself only recently taken shape. The explosion that created those hydrogen atoms, the specific nuclear reactions in that specific stellar furnace that produced the specific isotopes now moving through your veins, happened somewhere between 7 and 10 billion years ago, in a place and a time so remote from our own experience of the universe that the distance cannot be expressed in any unit of length or duration that means anything to a human being living on the surface of a small rocky planet in 2026. The oxygen atoms bonded to that hydrogen, the oxygen that completes the water molecule, that holds the hydrogen in its embrace and makes H2O rather than just H2. Those were assembled in the nuclear furnace of a dying red giant star so large that our entire solar system, from the sun to the outermost reaches of the Oort cloud, would have fit inside it with room to spare. A star that burned for billions of years, fusing lighter elements into heavier ones in its core, building up layer after layer of increasingly complex nuclear architecture, until the process reached iron, and iron could not be fused to release energy, and the star ran out of the only thing that had been holding it up, and it collapsed inward on itself in a fraction of a second, and then exploded outward with a force that briefly outshone the entire galaxy around it. The iron in your blood came from that explosion. The oxygen in your water came from the preceding stellar lifetime. The hydrogen came from something older still, from the first few minutes after the Big Bang, when the universe was dense enough and hot enough to fuse hydrogen nuclei out of the raw plasma of quarks and electrons that preceded them. Your hydrogen is as old as matter itself. It has been in the universe longer than any star has existed. It was part of the first generation of cosmic structures that formed after the beginning of everything. And those atoms have been cycling through this planet for 4.5 billion years. They were here before the oceans existed. They were locked in minerals, compressed into the crystal lattices of rocky asteroids that were still falling through the young solar system, gradually being swept up by a growing planet that had not yet fully decided what it was. They were here before the Earth had finished forming, before the last great collision that shaped our world had occurred, before the moon existed, before the solid ground under your feet had taken the form it now holds. They were here when the surface of this planet was a sea of magma, 2,000 kilometers deep, glowing white-hot under a sky choked with vaporized rock, a sky that had no oxygen in it and no water vapor that could survive long enough to fall as rain because the ground was too hot to hold it. They were here when the first rain fell on the first solid rock. They have been part of glaciers that buried entire continents under kilometers of ice, of rivers that carved canyons through stone, of clouds that formed and dissolved and formed again over an ocean that covered 80% of a world with no dry land anywhere. They have been breathed out by the first cell that ever divided, and drunk by the first animal that ever moved toward food, and evaporated into a sky that had not yet turned blue, because nothing was alive yet to produce the oxygen that makes our sky the color it is. The question of where the water came from. Where did the ocean come from? This is one of the most fundamental questions in planetary science, and it remains actively contested. The short answer that the ocean is water delivered to the Earth's surface from various sources over billions of years is technically correct, but explains almost nothing. The interesting question is where, specifically, the water came from, and in what proportions, and over what timescale. Let us approach this question from the beginning. The standard model of planetary formation, as we have already seen, suggests that the Earth formed in the inner solar system, in a region close to the Sun, where the temperature was too high for water ice to be stable. The boundary in the early solar system where water ice could persist, called the frost line or snow line, was located somewhere in the vicinity of the asteroid belt, between Mars and Jupiter. Inside this line, the material available for planetary formation was dry, rocks and metals, stripped of their volatile compounds by the heat of the young Sunday. Outside this line, water ice was abundant, incorporated into comets and the icy moons of the outer planets. The Earth formed inside the frost line. Therefore, the Earth should have formed dry. And yet here we are, with an ocean. There are essentially 4 ways that water could have arrived at the Earth's surface, and the relative importance of each is still being argued about by planetary scientists. The first is external delivery by comets. Comets are bodies of ice and rock originating in the outer solar system, the Kuiper belt, just beyond Neptune, and the Oort cloud, a vast spherical shell of cometary bodies, extending to the very outer edge of the solar system's gravitational influence. Comets are rich in water ice, which is why they produce the spectacular tails of vapor and dust that make them visible when they fall through the inner solar system and are warmed by the Sunday. During the late heavy bombardment, a period roughly between 4.1 and 3.8 billion years ago, when the orbital reorganization of the outer planets drove large numbers of cometary bodies into the inner solar system, enormous quantities of cometary material fell on the Earth. Each comet brought its payload of water ice. Over millions of years, this delivery could have added significant quantities of water to the Earth. The second is external delivery by asteroids, specifically by carbonaceous chondrite meteorites, a class of primitive, carbon-rich rocky bodies that formed in the outer part of the asteroid belt, beyond the frost line, where they could incorporate water into their mineral structure. Unlike the water in comets, which is present as ice, the water in carbonaceous chondrites is bound into the crystal structures of hydrated minerals, phyllosilicates, serpentine, chlorite. This water is locked in the rock chemically rather than physically, and it can survive the heating of an asteroid impact better than free water ice can. When a carbonaceous chondrite strikes the Earth, the impact energy releases the water from the minerals as steam. The third possibility, and this is where things get genuinely interesting, is that the water was already here, not delivered from outside after the Earth formed, but incorporated into the Earth's original building material. Some researchers have argued that even the rocky, relatively dry material of the inner solar system contained enough water in mineral form to account for a significant fraction of Earth's ocean, and that this water was simply sequestered in the mantle during the planet's formation and has been gradually released to the surface over billions of years through volcanic outgassing. The fourth possibility is a combination of the first 3, with different sources contributing different fractions at different times. To distinguish between these possibilities, scientists have turned to a clever chemical fingerprint. The blow that made the moon the impact that formed the moon is the most violent event in the history of the inhabited Earth, by which I mean, it is the most violent event that occurred on this planet in the time after its formation, but before the planet was sterilized and reset so completely that any meaningful connection to what came after was severed. We know it happened. We are less certain about the details. The evidence comes primarily from the moon itself, whose composition is strikingly similar to that of Earth's mantle, so similar that the most convincing explanation is that the moon was made largely from Earth material, ejected into orbit by a collision. The evidence also comes from the dynamics of the Earth-Moon system. The Moon's orbit, its rotational state, the inclination of Earth's axis, all of these things are consistent with a large oblique impact early in Earth's history. The impactor, the body that struck the proto-Earth, is given the name Theia in the scientific literature after the Titan, who was the mother of the Moon in Greek mythology. This naming reflects both the uncertainty and the importance of the object. We have no direct sample of Theia. We cannot analyze its composition directly. We can only reconstruct its properties from the consequences of the collision. Theia was probably roughly the size of Mars, a fully formed planet in its own right, having accreted from the same disk of material as the Earth, following a similar but slightly different orbital path around the young Sunday. For millions of years, Theia and the proto-Earth coexisted in similar orbits, without colliding the resonance of their orbital periods, keeping them separated. But the gravitational interactions of the growing solar system are complex, and over time, those interactions altered Theia's orbit slightly, just slightly, enough. The collision that followed was not like anything we have direct experience of. When two planetary bodies of significant mass collide at the velocities that orbital mechanics produces, the result is not a crater. It is not even what we normally mean by an explosion. The energies involved are so enormous that both bodies are effectively liquid, or rather, the distinction between solid and liquid loses meaning at these temperatures and pressures. The impact is more like the merging of two large drops of extremely hot and dense fluid, except that the fluid is rock and metal. In the hours during and immediately following the impact, the Earth-Theia system passed through a state that has been called a synestia, a rapidly rotating donut-shaped body of vaporized rock, with a rocky and metallic core at the center, and vast quantities of rock vapor in a disk extending outward. From the rock vapor in the outer parts of this disk, the Moon eventually condensed. From the remaining material in the inner part of the disk, the Earth eventually reformed. The impact reset every clock on the planet. Whatever thin crust had formed on the proto-Earth before the impact was destroyed. Whatever nascent atmosphere had begun to develop was either incorporated into the merged body or blown into space. Whatever trace amounts of water might have been present on or near the surface were vaporized so completely and so violently that no meaningful quantity could have survived. The Earth was returned to a state of being a molten ball of rock and metal, indistinguishable in its essential character from what it had been immediately after its formation, hundreds of millions of years earlier. The temperature at the surface of the post-impact Earth has been estimated at between 3,000 and 6,000 Kelvin. For reference, the surface of the Sun is about 5,800 Kelvin. The post-impact Earth was, briefly, comparable in surface temperature to the star that warms us. It was, in this sense, a second sun, a small, rocky, temporary second sun, glowing in the dark of the young solar system. At those temperatures, silicate rock does not merely melt, it vaporizes. The atmosphere immediately after the impact was not a gas in any conventional sense. It was a plasma of silicate molecules, a thick, opaque, intensely hot envelope of material that had recently been rock. The sky above the post-impact Earth was not dark. It was luminous with the radiation of heated rock vapor, a deep orange glow that would have been visible from a great distance. And then the cooling began. The post-impact Earth began to radiate energy into space. The rock vapor in the atmosphere began to condense, falling. At first, not as rain but as a rain of silicate droplets, tiny spheres of molten rock that fell through the lower atmosphere and added their heat to the already incandescent surface. Over tens of thousands of years, the silicate atmosphere thinned. The surface temperature dropped. A new secondary atmosphere began to form, this time dominated by carbon dioxide and nitrogen and water vapor, released by the continued outgassing of the cooling magma ocean below. The stage was being set for the arrival of the water, but not yet. Not for a long time yet. the magma ocean, and the long cooling. The magma ocean of the post-impact Earth is one of the least known periods in our planet's history, and also one of the most important. It lasted for millions of years. During this time, the entire surface of the Earth was liquid rock. Not lava in the sense that we mean when a volcano erupts. Lava is a specific type of rock in a specific state, cooled from magma and exposed to the surface, with a particular chemical composition and a particular behavior. The magma ocean of the early Earth was something more fundamental. It was the planet's interior, laid bare. It was the undifferentiated raw material of a world still in the process of becoming. At the top of the magma ocean, the surface was continuously disturbed. The impact of smaller asteroids and planetesimals, which continued at a reduced rate after the giant impact, sent waves across the liquid surface. Convective currents within the magma ocean, driven by the slow cooling from the top and the residual heat of the Earth's interior, created large-scale circulation patterns that would have been visible from space as slowly moving patches of lighter and darker material. The surface was not smooth. Below the surface, a process of immense importance was underway. Differentiation. The Earth's materials were sorting themselves by density. Iron and nickel, the densest materials, were sinking. Silicate minerals, lighter, were rising. This process, which had begun during the original accretion of the planet and been scrambled by the giant impact, was now proceeding in a body that was everywhere liquid and proceeding efficiently. The iron sinking to form the core was releasing gravitational potential energy as it fell. This energy, added to the residual heat of accretion and the giant impact, kept the magma ocean from cooling too quickly. The Earth was, in a sense, generating its own heat through the process of differentiation, but the cooling was inexorable. Heat, in the absence of insulation, always flows from hot to cold. The magma ocean was at thousands of degrees. Space is essentially at zero. Energy was constantly radiating from the surface of the Earth into the surrounding void. The thick atmosphere helped slow this process. Carbon dioxide and water vapor are greenhouse gases, and the early atmosphere was extraordinarily rich in both, so it trapped a great deal of the heat that the surface was trying to radiate away, but it could not stop the cooling entirely. Slowly, over millions of years, the surface temperature fell. At a temperature of roughly 1200 degrees Celsius, silicate minerals begin to crystallize from the melt. The first mineral to crystallize, at the hottest temperatures, is olivine, a magnesium iron silicate that forms in the deep interior of the magma ocean and, being denser than the surrounding melt, sinks. As the temperature continues to fall, other minerals crystallize in sequence: pyroxene, plagioclase feldspar, each one forming at the temperature at which its particular molecular architecture becomes more stable than the liquid state. This is the beginning of the crust. But this first crust was nothing like the crust we stand on today. It was fragile. It was temporary. It was constantly being disrupted by the convective movements of the magma beneath it. Where the convective currents rose, they brought up fresh hot material from below and melted through the thin, solid layer from underneath. Where they descended, they dragged pieces of the crust back down into the melt. The surface of the early Earth was in a constant state of making and breaking itself, producing a thin, unstable, temporary skin of solid rock that was immediately recycled. There were no continents. There were no ocean basins in the geomorphic sense, no deep depressions surrounded by elevated rims. The surface was one irregular topography, slightly raised in some places and slightly depressed in others, but without the fundamental distinction between thick, buoyant continental crust and thin, dense oceanic crust that characterizes the modern Earth. That distinction would take billions more years of geological processing to emerge, and there was, of course, no water. The water was coming. The physics and chemistry of the solar system made its arrival essentially inevitable. But the surface of the Earth during the magma ocean period was so hot that no water could remain liquid there, or even, for most of the period, remain as vapor in the atmosphere, rather than being lost to space by the intense ultraviolet radiation and solar wind of the young sun. The water was locked away. It was locked in the crystal structures of minerals falling as meteorites from the asteroid belt. It was locked in the mantle, incorporated into the silicate minerals that make up most of the Earth's volume. It was locked in comets in the outer solar system, waiting for the gravitational perturbations that would eventually send them falling toward the inner planets. And it was waiting, with the patience of physics, for the surface to cool enough to hold it. The faint young sun and the first atmosphere. There is a paradox at the heart of early Earth science, and it has been sitting there for decades, embarrassing our models and resisting easy resolution. It is called the faint young sun paradox, and it was first clearly articulated by the astronomer Carl Sagan and his colleague George Mullen in 1972. The paradox goes like this. We know from stellar physics that the sun has been gradually brightening over its lifetime. When the sun was young 4 billion years ago, it was approximately 70% as luminous as it is today. If you took the current Earth, with its current atmosphere and its current geography, and simply reduced the sun's output to 70% of its present value, the planet would freeze completely. The oceans would turn to ice. The ice would reflect more sunlight than liquid water, cooling the planet further until you reached a state called a snowball Earth, a fully frozen, white, highly reflective sphere. And yet the geological record of the early Earth shows liquid water. Not just a little liquid water, not just local pockets near volcanic vents, but a global ocean. Rock formations of the right age, in multiple locations around the world, show evidence of having been deposited in liquid water. Some of the most ancient sedimentary rocks that can only form from material deposited in water, are nearly 4 billion years old. The early Earth, with its faint young sun, somehow avoided being frozen. How? The answer is almost certainly the atmosphere. The early Earth's atmosphere was not our atmosphere. It was much thicker, much denser, and composed of gases that are far more effective greenhouse gases than our current atmospheric mixture. Carbon dioxide was present at concentrations hundreds of times higher than today. Methane, produced by volcanic activity, may have been present in significant quantities. Water vapor, which is itself a powerful greenhouse gas, was abundant in the lower atmosphere. These gases, in sufficient concentrations, can compensate for a weaker sun day. The greenhouse effect works by allowing sunlight to pass through the atmosphere and warm the surface, while trapping the longer wavelength infrared radiation that the surface then emits. The more greenhouse gases in the atmosphere, the more efficient this trapping, and the warmer the surface for any given solar input. The early Earth appears to have had enough greenhouse gases to keep its surface liquid, despite the faint young sun. But this creates a secondary problem. The carbon dioxide concentrations required to maintain a liquid ocean in the face of a sun 30% dimmer than today would have created a surface temperature far higher than what the geological record suggests. Some models require CO2 concentrations thousands of times higher than the present level. If those concentrations had actually existed, the early ocean would not just have been unfrozen, it would have been boiling. The truth, as usual, is somewhere in the middle and more complicated than either extreme. Recent research suggests that the early Earth's atmosphere was a complex mix of various greenhouse gases, methane, as well as carbon dioxide, and that some of these gases were far more effective at warming the planet than carbon dioxide alone. Additionally, the early Earth may have had a faster spinning rotation, which would have altered the global circulation patterns and the distribution of heat. And the geography of the early Earth, essentially no continental land masses, just a global ocean with scattered volcanic islands, would have created very different albedo reflectivity characteristics than the modern Earth. With all its ice-covered poles and continental interiors, We are still working out the details. What we know from the rock record is that liquid water existed on the Earth's surface at a time when the standard models say it shouldn't have been able to. This is not a failure of the models to identify a mechanism, it is simply that reality is more complex than our models, and that the early Earth found a way. This is, actually, a recurring theme in the history of the early Earth. The planet has a way of making liquid water exist, where the simple calculations say it shouldn't. The story of the early ocean is, in part, a story of water insisting on being present against the odds. The first atmosphere, thick, greenhouse-heavy, rich in volcanic gases, was the insulation that allowed the first ocean to form and persist. Without it, the water delivered to the surface would have frozen or been lost to space before it had a chance to accumulate. With it, something remarkable was about to become possible. The world before the world there is a name for the era we are going to, the Hadean. It is a geological eon, defined by its age from the formation of the Earth approximately 4.54 billion years ago to approximately 4 billion years ago, and named for a place rather than a phenomenon. Specifically, named for Hades, the ancient Greek word for the underworld. The word carries with it everything the ancient Greeks meant by it. A realm of the dead, a place beyond the reach of the living, a domain of darkness and heat and finality. The people who named this geological eon were geologists, not poets. They were using the word with deliberate precision, because the Hadean Earth was, by the standards of every living thing that has ever existed on this planet, a version of the underworld, not as mythology imagines it, with deliberate cruelty and the suffering of individual souls, as physics makes it. A world of such extreme conditions that the very molecules of life as we know it could not have existed on its surface. A world where the oceans we are used to thinking of as permanent features of our planet had not yet formed, where the sky was not blue but the color of a toxic chemical reaction, where the ground was not solid but a slowly cooling skin over a planet-wide ocean of liquid rock. This is where our story begins. But to understand the Hadean Earth, you first have to understand how the Earth formed. Not in the abstract sense of knowing that planets form from the accretion of material around young stars. Most educated people know this in the way they know that cells make up living things, as a fact that is true, but that has not been fully inhabited. You have to understand it concretely, in terms of what was actually happening, physically, to the material that would become the ground under your feet. The story begins 4.5 billion years ago in a region of one arm of the Milky Way galaxy, where a giant molecular cloud, a vast, diffuse collection of gas and dust, stretching across hundreds of light years, was slowly condensing under its own gravity. Molecular clouds are the nurseries of stars. They contain everything needed for stellar formation: hydrogen and helium in enormous quantities, traces of heavier elements produced by previous generations of stars and distributed through the galaxy by supernovae, complex organic molecules that form in the cold darkness between stars, and here and there, small regions where the density is slightly higher than average and the inward pull of gravity slightly exceeds the outward pressure of the gas. Something triggered the collapse of one such region. Perhaps the shockwave from a nearby supernova, pushing into the gas cloud and compressing it. Perhaps simply the slow accumulation of gravitational instability over millions of years. Whatever the cause, a region of the cloud began to collapse. As it collapsed, it heated up gravitational potential energy, converting to kinetic energy converting to heat. And as it heated and spun faster and faster, conservation of angular momentum, requiring the collapsing sphere to rotate as it shrank, it flattened into a disk. At the center of this disk, the density and temperature rose until nuclear fusion ignited. The sun was born. Around it, in the disk of remaining gas and dust, something different was happening. The material was not dense enough to ignite nuclear fusion. Instead, it began to clump. Tiny grains of dust, moving through the disk on their orbital paths around the young sun, collided with other grains. Sometimes they bounced off. Sometimes they stuck together. The ones that stuck together became slightly larger, and slightly larger objects have a slightly stronger gravitational pull, which means they are slightly better at attracting more material. Over tens of thousands of years, grains became pebbles, pebbles became boulders, boulders became planetesimals, irregular rocky bodies ranging from meters to hundreds of kilometers across, and planetesimals, having their own substantial gravity, began to dominate the process. A planetesimal moving through the disk sweeps up smaller material with its gravity, growing steadily larger. Larger planetesimals move more slowly relative to each other and are more likely to collide rather than miss. When they collide at relatively low velocities, they merge rather than fragment. The largest planetesimals become planetary embryos, moon-sized to Mars-sized bodies that have cleared significant regions of the disk of smaller material. And planetary embryos, in their turn, collide with each other in the final and most violent phase of planetary formation. This is how the Earth was made. Not gently, not gradually. Through a series of increasingly violent collisions between increasingly large bodies, each impact releasing enormous quantities of energy, each merger adding to the growing mass and the growing internal heat of the proto-Earth. The collisions were so energetic and so frequent and released so much heat that the forming Earth could not radiate the energy away fast enough. The surface never cooled between impacts. The heat accumulated. The entire growing planet remained molten. This was the first magma ocean, not the last. The forming Earth was a sphere of liquid rock and metal, slowly differentiating as the physics of density sorted the denser materials from the lighter ones. Iron and nickel, being the densest materials present, sank toward the center, forming the core. Lighter silicate minerals rose toward the surface, forming what would eventually become the mantle and crust. But this differentiation took place in a body that was entirely liquid, in a process that was violent and chaotic rather than orderly, and the resulting planet was thoroughly, uniformly, everywhere hot. The surface glowed. Not the red glow of lava that we see when volcanoes erupt, though that was there too. The surface of the early Earth, at its hottest, emitted a white light, the color of extreme heat, the color of something burning at temperatures where the electromagnetic radiation produced begins to peak in the visible range of the spectrum rather than the infrared. The early Earth was, in a literal sense, luminous. It shone with its own light. From space, it would have resembled a small star, more than the blue marble we see in photographs taken from the moon. Above this glowing surface, a thick envelope of gas, some outgassed from the cooling magma, some delivered by the continued rain of impactors, some vaporized from the impactors themselves upon collision, formed the first atmosphere. This atmosphere was nothing like the one we breathe. It was dense with carbon dioxide, carbon monoxide, nitrogen, water vapor, sulfur dioxide, and a complex mixture of other volcanic gases. There was no free oxygen. There was no nitrogen-oxygen balance that sustains aerobic life. There was no ozone layer to filter the ferocious, ultraviolet radiation of the young sun. The young sun itself was different from the sun we know. Paradoxically, it was both more active and less luminous. Its total energy output was perhaps 70% of what it is today, a fact that creates a famous puzzle in Earth science called the faint young sun paradox, which we will return to later. But its activity, the solar flares, the coronal mass ejections, the intensity of the solar wind, was far greater than today. The young sun was energetically volatile in the way that young things often are, producing eruptions that would dwarf anything we have seen in the recorded history of solar observation. In this environment, magma ocean, toxic atmosphere, violent young sun, continuous bombardment by asteroids and planetesimals, the Earth spent the first tens of millions of years of its existence. And then, Just as the planet might have been beginning to cool, just as the first hints of a surface crust might have been beginning to form, something happened that reset everything. Part 6. Water's fingerprints. Water is not simply H2O, or rather, it is H2O. But the H in H2O is not always the same. Hydrogen, the most abundant element in the universe, exists in several isotopic forms. The most common is ordinary hydrogen, a single proton, orbited by a single electron, with no neutrons in the nucleus. This is called protium, and it makes up more than 99.98% of all the hydrogen atoms in the universe. But a small fraction of hydrogen atoms have a neutron in their nucleus in addition to the proton. These are called deuterium atoms, heavy hydrogen. The water molecule made with 2 deuterium atoms instead of 2 ordinary hydrogen atoms is called heavy water, D2O. The ratio of deuterium to ordinary hydrogen in a sample of water is written DH, and it acts as a chemical fingerprint. Different places in the solar system have different DH ratios, and the specific DH ratio of a sample of water tells you approximately where that water formed. The reason for this is nuclear physics and the conditions of the early solar system. Deuterium forms preferentially in cold environments, in the cold molecular clouds of the interstellar medium. Chemical reactions preferentially incorporate deuterium into certain molecules. When the solar system formed, the DH ratio of water varied systematically with distance from the sun. Water farther from the sun, in colder regions, had higher DH ratios than water closer to the sun in warmer regions. Comets, which formed in the cold outer solar system, have higher DH ratios than the water in Earth's ocean. Carbonaceous chondrite meteorites, which formed in the outer part of the asteroid belt closer to the frost line, have DH ratios much closer to Earth's ocean. This is the key to the detective story. In 1986, scientists made the first precise measurements of the DH ratio of a comet's water, Halley's Comet. The ratio was approximately twice as high as in Earth's ocean water. This was a problem for the theory that comets had delivered Earth's oceans. If the ocean had been delivered primarily by comets like Halley's, the DH ratio of Earth's ocean would be much higher than it is. Subsequent measurements of other comets confirmed that most have DH ratios significantly higher than Earth's ocean, typically 2 to 3 times higher. In 2014, the Rosetta spacecraft, which successfully orbited and landed a probe on Comet 67P, Churyumov-Gerasimenko, after a 10-year journey through the solar system, measured the water in the comet's coma and found a DH ratio 3 times higher than Earth's ocean. The comets, at least the ones we have been able to measure, appear to have the wrong water for Earth's ocean. But there is a complication. In 2011, the Herschel Space Observatory measured the DH ratio of water in Comet Hartley 2, a comet from the Kuiper Belt rather than the Oort cloud, and found a ratio essentially identical to Earth's ocean. If Hartley 2 is representative of a class of comets that were particularly abundant in the early solar system, then cometary delivery might still have played a role. Meanwhile, measurements of carbonaceous chondrite meteorites have consistently found DH ratios close to or indistinguishable from Earth's ocean. The CI chondrites, the most primitive and chemically unaltered class of carbonaceous chondrites, have DH ratios that match Earth's ocean almost perfectly. This has led most researchers to conclude that carbonaceous chondrites, or material compositionally similar to them, are the primary source of Earth's ocean water. But how much of Earth's water came from the mantle, having been incorporated into the original building material? Recent measurements of ancient volcanic rocks from deep in the mantle material that has not been significantly altered since the early Archean, billions of years ago, suggest that the mantle contains more water than we thought, with DH ratios slightly different from the ocean. This is consistent with the idea that some fraction of Earth's water, perhaps 10 to 40%, depending on the model, was already present in the mantle before the late heavy bombardment and has been slowly released to the surface through volcanic outgassing over the billions of years since. The emerging consensus, which is more nuanced than the old debate between comets and asteroids, is something like this. Earth's water has multiple origins. A significant fraction, perhaps the majority, was delivered by carbonaceous chondrite-type asteroids, or was already present in the Earth's original building material from asteroid belt sources. A smaller fraction may have been delivered by comets, and an ongoing contribution from volcanic outgassing of mantle water has maintained and slightly augmented the ocean throughout Earth's history. But the argument is not fully settled. The discovery that even the mantle, far below the ocean, holds vast quantities of water has complicated the picture in ways that researchers are still working through. Part 7. The Hidden Ocean. Inside the Earth in 2014. A remarkable paper was published in the journal Science. It announced the discovery, inside a diamond recovered from the Juarez mine in Mato Grosso, Brazil, of a tiny inclusion of a mineral called ringwoodite. Diamonds form under extraordinary pressure, deep in the Earth's mantle, typically at depths of between 100 and 200 kilometers, where the pressure is roughly 50,000 atmospheres. The diamond in question had been carried to the surface by a volcanic eruption, in the way that all diamonds reach the surface, encased in a type of volcanic rock called kimberlite, carried upward in a rapid eruption of deep mantle material. But this particular diamond was special because of what was trapped inside it. Ringwoodite is a mineral that only exists under the extreme pressures found in the MO transition zone of the Earth's mantle. At depths of between approximately 400 and 600 kilometers. At lower pressures, its crystal structure is unstable and it transforms into other minerals. At higher pressures, it transforms again. Ringwoodite exists only in this narrow pressure window, and because it can only exist at those depths, the presence of ringwoodite inside a diamond is evidence that the diamond, and whatever was trapped inside it, formed at unusual depth. The ringwoodite in the Brazilian diamond was special for another reason. It contained water. About 1.5% of its weight was water, incorporated into the crystal structure of the mineral, as hydroxyl groups OH- and ions slotted into the spaces between the oxygen and magnesium atoms of the mineral's lattice. This was not a surprise in itself. It had been known for some time, from laboratory experiments that recreated the conditions of the mantle transition zone, that ringwoodite could incorporate water into its crystal structure. But the question of whether the actual mantle transition zone, hundreds of kilometers below our feet, extending around the entire globe, actually contained water, or was dry like the upper mantle was once thought to be, had been unresolved. The ringwoodite inclusion settled the question, or at least pointed strongly in one direction. If the ringwoodite in this one tiny sample had 1.5% water by weight, then the mantle transition zone, which is made largely of ringwoodite, and its related minerals, might also contain significant quantities of water. The transition zone has a mass of roughly 1 billion cubic kilometers of rock. 1.5% of that, by weight, would be an ocean, a large ocean. Potentially an ocean larger than all the water on the surface of the Earth combined. The subsequent seismic evidence has supported this idea. Seismic waves, the waves of pressure that travel through the Earth's interior following earthquakes, travel at different speeds through rock that contains water than through dry rock. Analysis of seismic data from the transition zone, conducted since the 2014 paper, suggests that the transition zone is indeed significantly hydrated, not bone dry, as the simplest models had predicted. The implications of this are difficult to overstate. If the transition zone contains as much water as the preliminary evidence suggests, then the history of the ocean is not primarily a history of water being delivered from outside the Earth. It is a history of water being exhaled from the Earth's interior. The volcanic gases that have been building up the atmosphere and ocean since the beginning of Earth's history include substantial quantities of water vapor, and this water vapor comes ultimately from the water locked in the 5 mantle minerals. Every time a volcano erupts, it releases not just lava and gases, but also water. This water was incorporated into the magma as it formed, deep in the mantle, from minerals that had water bound into their crystal structures. As the magma rises toward the surface, the decreasing pressure allows the water to escape as vapor. The eruption disperses this water vapor into the atmosphere, where it eventually condenses and falls as rain and adds to the ocean. Over the 4.5 billion years of Earth's geological history, this process has operated continuously. The mantle is slowly exhaling its water. The ocean is, in this sense, the breath of the planet. And the planet breathes very slowly. The current rate of volcanic outgassing of water is estimated at roughly 1 cubic kilometer of water per year. A significant quantity on a human timescale, but tiny compared to the volume of the ocean. At this rate, it would take billions of years to outgas the entire ocean, which is, in fact, roughly how long the Earth has been doing it. But the rate was not always this slow. In the early Earth, geological activity was far more intense. The crust was thinner, the mantle hotter, the convective processes that drive volcanism operating faster and more energetically. The rate of volcanic outgassing in the Hadean was many times higher than today. The early ocean was built, in significant part, from this ancient volcanic exhalation. The Earth's ocean is the exhalation of a planet. The water in your body has, very likely, been through the mantle. It has been part of a mineral crystal deep inside the Earth, released by a volcanic eruption, rained down through an ancient atmosphere, incorporated into an ancient ocean, cycled through living things, evaporated, rained again, flowed through rivers, soaked into soil, been drunk by animals, breathed out, and done it all over again thousands of times across billions of years. The water in you is not from the ocean. In a very fundamental sense, the ocean is from the same place you are. Part 8. The Zircon Record in the Earliest Water. The oldest rocks on Earth are found in a few scattered locations around the world, where the ancient Archean crust has survived the relentless geological recycling that has destroyed most of the Frand. Early record. The Acasta gneiss in Canada, the Itzhak gneiss complex in Greenland, the Narrier-Terranais in Western Australia. These rocks are approximately 4 billion years old, young enough to have formed after the worst of the Hadean bombardment, but old enough to tell us something about the very early Earth. But they are not the oldest material we have. For that, we turn to a mineral called zircon. Zircon is a silicate mineral, zirconium silicate, ZrSiO, that forms in cooling magma and is essentially impervious to the chemical and physical processes that destroy most other minerals over geological time. While the rocks around it weather and metamorphose and melt and reform over billions of years, zircon grains persist. They are carried along as sedimentary particles, incorporated into new rocks, altered in their external appearance, but not in their internal chemical composition. Their crystal structure, once formed, is essentially inert over geological timescales. This makes zircon invaluable to geologists because zircon incorporates uranium into its crystal structure when it forms and excludes lead. Since uranium radioactively decays into lead at a precisely known rate, a zircon crystal is essentially a clock that starts when it crystallizes and runs without interruption for as long as the crystal remains intact. By measuring the ratio of uranium to lead in a zircon crystal, geologists can determine with remarkable precision when that crystal formed. The oldest zircon crystals so far identified come from the Jack Hills of Western Australia, a remote and rather featureless range of low hills in the western part of the continent. These crystals were not found in their original rock. The rock that surrounded them when they first crystallized has long since been destroyed and recycled. Instead, they were found as detrital grains in much younger sedimentary rocks, tiny mineral crystals that had survived the destruction of their parent rock and been incorporated into newer deposits. The oldest of the Jack Hill zircons has been dated to 4.404 billion years ago, the oldest material of terrestrial origin ever identified. A crystal that formed when the Earth was barely 130 million years old. And these crystals contain information about the conditions of the early Earth. Within the crystal structure of zircon, in addition to uranium and lead, there is a tiny amount of oxygen, the oxygen that is part of the silicate mineral itself. The ratio of two isotopes of oxygen, oxygen 1,6 and oxygen 1,8, is sensitive to the temperature and conditions under which the mineral formed. Specifically, it is sensitive to whether liquid water was present. When oxygen is cycled through liquid water, as happens when rocks are weathered by rain and rivers and ocean water, the oxygen 1,8 to oxygen 1,6 ratio in the resulting minerals is different from what it would be in minerals formed in a completely dry, magmatic environment. Water, because of the slight difference in mass between oxygen 1,6 and oxygen 1,8, preferentially incorporates oxygen 1,6, leaving the remaining rock enriched in oxygen 1,8. The Jack Hill zircons have oxygen isotope ratios consistent with having formed in the presence of liquid water. They show the signature of water-rock interaction at the surface. They suggest that even at 4.4 billion years ago, within the first 100 million years of Earth's history, in the era that we call the Hadean, there was liquid water at or near the Earth's surface. This is a remarkable result. It means that the ocean, or at least the beginnings of the ocean, water in some form at the surface, may have formed much earlier than we had assumed. The standard picture of the Hadean Earth as uniformly hellish, uniformly covered in magma, with no surface water for the first billion years, appears to be wrong. How can this be reconciled with what we know about the magma ocean and the Theia impact? The answer may lie in the timeline. The giant impact is thought to have occurred approximately 4.5 billion years ago. The magma ocean it produced may have cooled more rapidly than previously thought. Some models now suggest that the initial magma ocean could have solidified within as little as 10 million years, rather than the hundreds of millions of years that older models assumed. And the water outgassed from the cooling magma, plus whatever water was delivered by the continued rain of carbonaceous asteroids, could have accumulated on the surface very quickly. The Jack Hill zircons suggest that this happened, that the surface had liquid water, at least intermittently, very early in Earth's history. That the catastrophe of the Theia impact was followed, much more quickly than we had thought, by the beginning of the ocean. The ocean did not wait. The late heavy bombardment. The early ocean did not form once and remain stable. The first few 100 million years of its existence were interrupted repeatedly by impacts of catastrophic scale events that may have partially or completely vaporized the early ocean, reset the surface conditions, and forced the water to accumulate again. This period is called the late heavy bombardment, and its reality and timing are still debated by planetary scientists. What we know with reasonable confidence is that between approximately 4.1 and 3.8 billion years ago, a period that corresponds to some of the oldest clear evidence of liquid water on Earth's surface, Moon was heavily bombarded by asteroids and other impactors. The evidence is the Moon's cratered surface. The large basins that dominate the near side of the Moon, Mare Imbrium, Mare Serenitatis, Oceanus Procellarum, appear to have formed during this period. Their floors later flooded by volcanic lava that gives them their characteristic dark, relatively smooth appearance. The cause of the late heavy bombardment is thought to be the Great Instability, a period of orbital reorganization among the giant planets, When Jupiter and Saturn passed through a resonance that caused Neptune and Uranus to migrate outward. As these planets moved, their gravitational influence disrupted the populations of small bodies in the outer solar system, sending large numbers of comets and asteroids on orbits that intersected with the inner solar system. The Earth, with its larger gravitational cross-section and its proximity to the asteroid belt, would have received far more impacts than the Moon during this period. The flux of impactors onto the Earth has been estimated to have been 10 to 30 times greater than the lunar flux, depending on the model. This implies a period of intense bombardment, not the constant rain of the early accretion period, but repeated large impacts, each one capable of having significant effects on the surface. The question is, how large were these impacts, and what did they do to the early ocean? Models of impact sterilization suggest that a single large impactor, roughly 500 kilometers in diameter striking the early Earth, could have generated enough heat to evaporate the entire ocean. The energy of the impact, distributed through the ocean and the atmosphere, would have been sufficient to raise the temperature of all the surface water above the boiling point and maintain it there for a period of years to decades. The ocean would have been replaced by a thick, hot steam atmosphere, which would eventually have cooled and rained back down. There were probably several impacts of this scale during the late heavy bombardment. This means that the early ocean was not a stable, permanent feature of the Earth. It was a dynamic, contested body of water, repeatedly evaporated and reconstituted, repeatedly reset. The geological record of this period is so sparse that we cannot trace each evaporation and reformation event individually, but the physics tells us that they happened, and yet the early ocean persisted. Every time it was vaporized, it rained back down. Every time the surface temperature dropped below the boiling point of water, the steam that had replaced the ocean condensed and fell as rain. The ocean reformed. It may have been saltier after each reformation, since the impact vaporization of water preferentially loses some of the lighter atmospheric species to space while retaining the dissolved minerals. It may have been hotter after each major impact, as the heat generated by the impact slowly dissipated, but it reformed. The persistence of liquid water on the early Earth, in the face of repeated large impacts, is one of the things that makes our planet's history remarkable. The ocean is a remarkable thing precisely because it kept coming back. It was not destroyed by the bombardment. It was repeatedly reformed by the same processes: volcanic outgassing, asteroid delivery, condensation of atmospheric water vapor that had formed it in the first place. The early Earth is not a story of a world that achieved a stable, hospitable state and then maintained it. It is a story of a world that was repeatedly knocked back toward hostility and repeatedly recovered. The ocean is not simply a permanent feature of the Earth. It is a permanent feature of the Earth that has had to be rebuilt again and again from the first principles of physics and chemistry. That kind of resilience does not suggest a fragile accident. It suggests a tendency, an inclination, something that the physics of this particular planet, with this particular chemistry and this particular position in this particular solar system, was always going to produce. The water kept coming back because the conditions for water kept being met. The first rain that stayed. There is a moment in the history of the early Earth that we cannot date precisely. We cannot point to a specific geological formation and say, here, this is where the ocean became permanent. We cannot identify the exact moment when the last reformation of the ocean, after the last major bombardment event, gave way to the continuous, uninterrupted ocean that has existed ever since. But we can reason toward it. The late heavy bombardment ended, approximately 3.8 billion years ago. The geological record from shortly after this time, the oldest clearly preserved rocks, the Archean formations of Greenland and Canada and Australia, shows evidence of liquid water at the surface. Sedimentary rocks formed in shallow water. Chemical sediments deposited from solution. Pillow lavas, which form when volcanic material erupts underwater. The record is unambiguous. By approximately 3.8 to 4 billion years ago, there was a stable, persistent ocean. The transition from the intermittent, repeatedly vaporized early ocean to the permanent ocean of the Archean was not, most likely, a sudden event. It was a gradual shift in the statistics of impact events. As the late heavy bombardment wound down, the frequency and scale of large impacts decreased. The largest impactors had already hit, or had been swept up by the growing planets and moons, or had been flung out of the solar system entirely by gravitational interactions. The remaining population of impactors was smaller and less frequent. At some point, approximately 3.8 to 4 billion years ago, the frequency of large impacts dropped below the threshold where the ocean could be globally vaporized. Smaller impacts could still cause local disruption, could still send enormous tsunamis across the ocean, could still disrupt the surface chemistry in local regions. But they could no longer evaporate the entire ocean, and so the ocean remained. That transition from an ocean that was repeatedly evaporated to an ocean that was permanently present is one of the most important events in the history of this planet. Not because of what happened to the ocean itself, but because of what it made possible. A permanent ocean, stable over geological time, provides a fundamentally different set of opportunities for chemistry than an intermittent ocean that repeatedly evaporates and reforms. Stable liquid water provides a medium in which complex chemistry can proceed continuously, building up intermediate products that would be destroyed or reset by an evaporation event. It provides a heat reservoir that smooths out temperature fluctuations and maintains relatively stable surface conditions over long periods. It provides a delivery mechanism for dissolved minerals from the interior to the surface, and a mechanism for cycling those minerals through the system. It provides, in short, the conditions for the emergence of life. Not life itself that would require additional steps, some of which we understand and some of which we do not. But the permanent ocean was the prerequisite, the canvas on which everything that followed was painted. The first rain that stayed, the moment when the ocean became permanent, was the beginning of the world as we know it. The early ocean's chemistry, the ocean that had established itself by approximately 3.8 billion years ago, was nothing like the ocean we know. Begin with the color. The modern ocean is blue, a consequence of the way water molecules absorb red and infrared light and scatter blue light. This effect is real and would have applied to the early ocean as well. But the early ocean was also full of dissolved minerals that would have given it a color distinct from the clear blue we associate with the deep modern ocean. The most important of these was iron. Iron is present in the crust and mantle in large quantities, and in the early Earth, with no free oxygen in the atmosphere or ocean, it remained dissolved in the seawater rather than precipitating out as iron oxides rust. The early ocean was an iron-rich solution, not dramatically different in color from what you might get by dissolving significant quantities of iron-containing minerals in water. A slightly murky, slightly greenish or brownish hue, depending on the concentration. This iron would eventually become one of the most important signals of the transition from the pre-life ocean to the ocean affected by life. The banded iron formations, the great geological deposits of alternating iron-rich and iron-poor sedimentary layers that are found in ancient rock formations around the world, record the gradual oxygenation of ocean by photosynthetic life. As life began producing oxygen, the oxygen reacted with the dissolved iron in the seawater, precipitating it out as iron oxides that settled to the seafloor. The banded pattern reflects a fluctuating relationship between oxygen production and iron availability over billions of years. But in the pre-life ocean, all that iron was still in solution. The ocean was iron-rich in a way that would be toxic to most modern marine life. The temperature of the early ocean was higher than today. Estimates vary widely. The isotopic record is ambiguous and subject to multiple interpretations, but values in the range of 40 to 80 degrees Celsius for the surface ocean of the early Archean are plausible. This is warmer than any modern ocean, warmer than comfortable bathing temperature for most humans, but well within the range that certain extremophilic bacteria today can not only tolerate, but actively prefer. The salinity of the early ocean was probably higher than today. The volcanic activity that produced the early ocean's water also produced large quantities of dissolved minerals: sodium, chloride, calcium, magnesium, potassium that dissolved in the water and did not cycle back into the crust as efficiently as they would in a world with full plate tectonics operating. Some models suggest the early ocean was significantly saltier than the modern ocean. The pH, the acidity, or alkalinity was also different. The early atmosphere's high carbon dioxide content would have dissolved into the ocean to form carbonic acid, driving the pH of the surface ocean lower, more acidic than today. At the same time, the volcanic outgassing of alkaline minerals could have partially buffered this acidity. The net result was probably a somewhat acidic early ocean, though the magnitude is uncertain. And there was no oxygen dissolved in the water. This bears repeating because it is so fundamental to the nature of the early ocean. The modern ocean contains dissolved oxygen delivered from the atmosphere, which itself is approximately 21% oxygen, and this dissolved oxygen is used by nearly all complex life in the ocean to power their metabolism. Remove the dissolved oxygen from the modern ocean and almost everything living in it would die. The early ocean had essentially no dissolved oxygen. The atmosphere had essentially no free oxygen. The chemistry of the early ocean was reducing in the chemical sense. The opposite of oxidizing in this chemistry is alien to nearly everything we call life today. The exceptions are the deep-sea anaerobes, the microbes that live in the absence of oxygen and use other chemical reactions to power their metabolism. These organisms, which are found today in the deepest and most chemically extreme environments on Earth, in the sediments of the ocean floor, in hydrothermal vents, in sulfur-rich environments, are the most direct descendants we have of the first life. They are the remnants, in some sense, of the metabolic world that the early ocean made possible. The early ocean was alien. It was hot and iron-rich and sulfur-rich and acidic and devoid of oxygen. It was, by the standards of the world we live in, hostile. And it was in this alien, hostile ocean that life began. The hydrothermal vents beneath the early ocean, the geological processes that we now call plate tectonics, were beginning to operate, though in a form different from the plate tectonics of the modern Earth. The modern Earth's crust is divided into a series of rigid plates that move relative to each other, driven by convection in the underlying mantle. Where plates diverge at mid-ocean ridges, new crust is created from magma rising up from below. Where plates converge at subduction zones, old dense oceanic crust is forced back down into the mantle and reabsorbed. This process drives volcanism, creates mountain ranges, builds and destroys continents, and circulates the Earth's interior materials on timescales of hundreds of millions of years. In the early Earth, this process was likely operating differently. The mantle was hotter, the plates thinner and more numerous, the rate of new crust creation higher, and the rate of subduction faster. There may not have been the large, stable tectonic plates of the modern Earth. Instead, the early crust may have been more like a thick, sluggish lava flow continuously produced by volcanism, continuously recycled back into the mantle, without the discrete plate boundaries of the modern system. But whatever the details of the early tectonic regime, one consequence was certain. There were hydrothermal vents. Hydrothermal vents are places where seawater seeps down into cracks in the ocean crust, is heated by the underlying magma to temperatures of hundreds of degrees Celsius, and then is expelled back into the ocean through chimney-like structures. The expelled water carries with it a rich cargo of dissolved minerals, sulfur, iron, manganese, zinc, copper, and a host of others leached from the rock during the transit through the crust. When this hot, mineral-rich water meets the cold ocean water above the vent, the minerals precipitate out of solution, forming the characteristic plumes of dark particles that give the most familiar type of hydrothermal vent its name, the black smoker. The discovery of hydrothermal vents in 1977 by the crew of the submersible Alvin diving on the Galapagos Rift was one of the most significant discoveries in the history of biology. The reason was not the vents themselves. Geologists had predicted their existence for years. The reason was what was living around them. The water around the vents was hot, acidic, and rich in hydrogen sulfide, a toxic gas that is lethal to most aerobic organisms. By every prior expectation, the vents should have been sterile. Instead, they were teeming with life. Tube worms reaching 2 meters in length, clams the size of dinner plates, mats of white bacteria coating every surface, shrimp clustered so densely around the vent openings that they formed living carpets. This life was not drawing energy from the Sunday. The vents were far too deep, over 2 kilometers, for sunlight to penetrate. Instead, the life around the vents was powered by chemosynthesis, the oxidation of hydrogen sulfide by bacteria, using the chemical energy of this reaction to fix carbon dioxide into organic molecules, just as photosynthetic organisms use light energy to fix carbon dioxide. The chemosynthetic bacteria at the base of the vent food web were doing for hydrogen sulfide and CO2 what plants do for sunlight and CO2. Life, it turned out, did not need the sun. This discovery had profound implications for the origin of life. The hydrothermal vents provided several things that are thought to be essential for the emergence of life. They provided chemical energy. The gradient between the hot, sulfur-rich vent fluid and the cold, sulfur-poor ocean water is a source of free energy that can drive chemical reactions. They provided mineral surfaces. The walls of the vent chimneys are rich in iron sulfide and other minerals that can catalyze chemical reactions, acting as primitive versions of the enzymes that modern life uses. They provided a protected environment. The pores and channels within the vent chimneys could have concentrated organic molecules rather than allowing them to diffuse away into the vast volume of the ocean. And they provided something else, a gradient. The difference between the inside and outside of the vent chimneys is not just a temperature gradient or a chemical gradient. It is an electrochemical gradient, a difference in the concentration of hydrogen ions, driving a potential difference across the barrier. And hydrogen ion gradients across membranes are exactly what living cells use to generate energy. In the modern cell, the mitochondria, the organelles that produce ATP, the universal energy currency of biology, work by establishing a hydrogen ion gradient across their inner membrane and then harvesting the energy released as those ions flow back through gradient. The hydrothermal vent provides this gradient for free. It is a geological proton motive force, the same mechanism that life uses for energy, produced without any biological machinery. The hypothesis that life originated at alkaline hydrothermal vents, not the black smokers, but a different type of vent called a white smoker, which produces cooler, more alkaline fluid, has become one of the leading candidates for explaining the origin of life. The white smokers produce a fluid that is alkaline and rich in hydrogen gas, which creates a strong electrochemical gradient across the vent wall in contact with the slightly acidic, carbon dioxide-rich early ocean. This gradient is not just a source of free energy. It is structurally analogous to the gradient that modern life uses. In the pores of these vent chimneys, the earliest proto-life may have emerged, not as fully formed cells, but as simple systems, mineral pores acting as primitive cell compartments, iron sulfide catalysts acting as primitive enzymes, simple metabolic reactions using the available chemical energy to fix CO2 and produce organic molecules. Over time, these systems became more complex. They developed better ways of capturing chemical energy. They developed ways of encoding information about their successful configurations, the first steps toward what would eventually become the genetic code. They developed membranes that could maintain the internal chemistry of the cell separate from the external chemistry of the ocean. Eventually, they became cells. Part 13. The first life in the ocean it inhabited. The question of when life began is one of the most contentious in all of science. The oldest unambiguous evidence of life on Earth comes from rocks approximately 3.5 billion years old. In the apex chert, a formation in Western Australia, structures have been found that resemble microbial fossils, tiny filaments of carbon in a form consistent with ancient bacteria. In South Africa and in Greenland, other formations of similar age show chemical signatures, isotopic ratios of carbon that are consistent with biological processes. But the interpretation of these ancient traces is disputed. The structures in the apex chert, initially described as bacterial fossils in the 1990s, were subsequently challenged by other researchers who argued that the structures could be the result of non-biological processes, mineral crystallization, hydrothermal alteration, purely geological chemistry. The debate has never been fully resolved. More recently, evidence has been found for life at even earlier dates. In 2016, a study reported finding possible traces of life in rocks from the Isua Formation in Greenland, dated to approximately 3.7 billion years ago. These were not fossil cells, but rather chemical traces, carbon isotope ratios in carbonate rocks that are consistent with biological carbon fixation. In 2017, another study reported finding possible microbial fossils in rocks from the Nouveau-Agetuk Formation in Quebec, Canada, which may be up to 4.28 billion years old. Though the dating of these rocks and the biological interpretation of the structures within them are both highly disputed, the honest answer is that we do not know exactly when life began. We know that by approximately 3.5 billion years ago, something recognizably alive was present on Earth. We know that the conditions for life, liquid water, chemical energy sources, a supply of carbon-containing molecules, existed from very early in Earth's history. And we know that the transition from non-living chemistry to living systems must have occurred somewhere in the time between the stabilization of the ocean and the earliest clear evidence of life. What we can say is that the ocean was the necessary precondition. Without liquid water, life as we know it cannot exist. The chemistry of life is aqueous chemistry, chemical reactions in solution, driven by the movement of molecules dissolved in water. The folding of proteins, the replication of nucleic acids, the transport of molecules across cell membranes, the generation of energy through electrochemical gradients, all of these depend on water as the universal solvent and medium. The ocean did not create life, but life could not have come into existence without the ocean. The early ocean provided the water and the chemistry. It provided the dissolved minerals that would become the first structural and catalytic materials of proto-life. It provided the energy gradients at the hydrothermal vents that drove the first metabolic reactions. It provided the physical environment, the microscopic pores and channels of the vent chimneys that could concentrate and contain the early chemical reactions. And once life began, the ocean provided the means by which it spread. The first living things, whatever they were, whatever exactly we mean by that word in the context of a transition that probably took millions of years and was not a discrete event, but a gradual process, existed in the ocean. They were chemical systems, embedded in the ocean, using the ocean's resources, interacting with the ocean's chemistry. They were, in a very real sense, made of the ocean. And then they began to change it. Part 14. What life did to the ocean. The relationship between life and the ocean is not a one-way relationship. The ocean shaped life by providing the conditions in which life evolved and placing constraints on what forms of life could survive. But life also shaped the ocean by changing its chemistry, its biology, and ultimately its physics. The most dramatic transformation was the oxygenation of the ocean. Before life began producing oxygen, the ocean was chemically reducing. Free oxygen was essentially absent. The chemistry that operated in the ocean in the absence of oxygen was sulfur chemistry, iron chemistry, hydrogen chemistry. The organisms that lived in this ocean, assuming they existed before the Great Oxidation Event, were anaerobes, organisms that live and metabolize without oxygen, using other chemical reactions instead. The transition to an oxygen-rich ocean was driven by the evolution of photosynthesis. Specifically, oxygenic photosynthesis, the type of photosynthesis that splits water molecules to release oxygen. This is the type of photosynthesis used by plants, algae, and cyanobacteria. It is the type that produces the oxygen in our atmosphere. And it evolved, as best we can tell, around 2.7 to 3 billion years ago, in ancestors of the modern cyanobacteria. The emergence of oxygenic photosynthesis was arguably the most consequential evolutionary innovation in the history of life on Earth. It provided a new source of energy, sunlight, that was vastly more abundant than the chemical energy sources available at hydrothermal vents. It allowed life to colonize the surface ocean where sunlight was available, and it produced, as a metabolic waste product, oxygen, a gas that was toxic to most of the anaerobic life that had preceded it, and that would go on to transform the chemistry of the ocean and the atmosphere. The transition from an anoxic to an oxygenated ocean, Great Oxidation Event, which is thought to have occurred approximately 2.4 billion years ago, was one of the most significant environmental changes in the history of the Earth. It was catastrophic for the anaerobic organisms that had dominated the ocean for more than 1 billion years. For them, the rising levels of oxygen were not a gift, but a poison, a waste product of a metabolic innovation that was transforming their world. But for the organisms that evolved to use oxygen to incorporate it into their metabolism, to use the oxidation of organic molecules by oxygen to extract energy far more efficiently than any anaerobic process could, the oxygenation of the ocean was an opportunity of extraordinary proportions. Aerobic metabolism extracts roughly 15 times more energy from the same quantity of food as anaerobic metabolism. The access to this energy source was a prerequisite for the evolution of complex, multicellular life. Without the Great Oxidation Event, there would be no animals, no plants, no fungi, no complex life of any kind, and the Great Oxidation Event could not have occurred without the ocean. The dissolved iron in the pre-oxidation ocean reacted with the oxygen produced by the early cyanobacteria, locking it into iron oxides that precipitated to the seafloor the banded iron formations. For hundreds of millions of years, this iron acted as a buffer, absorbing the oxygen produced by photosynthesis and preventing it from accumulating in the ocean or the atmosphere. Only when the dissolved iron in the ocean had been substantially depleted, had been mostly precipitated into the banded iron formations, could the oxygen begin to accumulate in the water and the air. The ocean, by buffering the oxygen with its dissolved iron, delayed the oxygenation of the atmosphere by hundreds of millions of years. During that delay, the cyanobacteria that were producing the oxygen were evolving and diversifying, filling the ocean, spreading to every environment where sunlight could reach. By the time the ocean's iron buffer was exhausted, the oxygen-producing organisms were so abundant and so efficient that the resulting oxygenation was rapid, at least rapid in geological terms. The ocean made the oxygen revolution possible by controlling the pace at which it occurred. The ocean, in this sense, shaped the course of evolution. Part 15. The Deep Time of the Ocean. Let us pause for a moment and try to hold the full scope of what we have been exploring. The ocean has existed for approximately 4 billion years. The Earth has existed for approximately 4.5 billion years. The ocean is, in other words, as old as nearly everything about the Earth that we think of as permanent. 4 billion years is a number that the human mind cannot truly comprehend. We can say it, but we cannot feel it. The entirety of recorded human history, every civilization, every empire, every discovery, every war, every artistic and scientific achievement spans approximately 5,000 years. The ocean is 800,000 times older than the entirety of human history. Let us try to scale this differently. If the 4 billion-year history of the ocean were compressed into a single year, beginning on January 1st and ending at midnight on December 31st, then each month of this compressed year would represent approximately 330 million years of actual time. Each day would represent approximately 11 million years. Each hour would represent approximately 450,000 years. On this scale, life first appeared roughly at the beginning of February. The first complex cells, with nuclei and internal organelles, appeared somewhere around October. The Cambrian explosion of animal life, the event that produced most of the major body plans of modern animals, happened in the third week of November. The dinosaurs appeared on December 10th. The asteroid that killed the non-avian dinosaurs struck on December 26th. And the entirety of modern human history, the last 5,000 years, happened in the last 2 seconds before midnight on December 31st. In those terms, the first ocean, the topic of this documentary, occupied the first month, January. A month of magma oceans and giant impacts, and the late heavy bombardment, and the first fragile attempts of chemistry to organize itself into something living. And that month shaped everything that followed. The decisions made by the chemistry of the early ocean, which minerals dissolved, which reactions proceeded, where the hydrothermal vents were active, what the temperature and pH and salinity were, constrained the possibilities available to the first life. The first life, in turn, modified the ocean's chemistry, constraining the possibilities available to later life. The ocean has been evolving continuously, shaped by geology and biology in equal measure, for 4 billion years. The ocean we have today, the blue, oxygen-rich, teeming with life ocean, is the result of all 4 billion years of that evolution. It is not the original ocean. It is not even close to the original ocean. It is the original ocean, transformed beyond recognition by the processes of geology and biology. And yet there is a continuity. The same water molecules that fell on the cooling basalt of the early Earth 4 billion years ago are still in the ocean today. The same atoms of carbon that were dissolved in the early ocean as CO2 have been cycled through living things thousands of times and are now in the tissues of marine organisms. The same calcium ions that were leached from the early basalt by acid rain are now in the shells of mollusks. The ocean is old, but it is not dead. It is a living archive of everything that has happened on this planet for the last 4 billion years. Part 16. The ocean that the early Earth built the Archean Eon, the time from approximately 4 billion to 2.5 billion years ago, is the period during which the permanent ocean established itself. The first life emerged and diversified, and the long process of transforming the Earth's surface from a volcanic hellscape into a world capable of supporting complex life began. The Archean Ocean was a world of shadows and heat, and iron-stained water, and the first green mats of photosynthetic life clinging to the sunlit surfaces of underwater rocks. The geography of the Archean world was different from anything that exists today. There were no large continents. The process of forming thick, buoyant continental crust by the melting and remelting of oceanic crust at subduction zones, which gradually separates out the lighter minerals and builds up thick blocks of granite composition rock, was still in its early stages. The land that existed was primarily low-lying volcanic islands and plateaus, the products of large magmatic provinces, regions where enormous quantities of magma were erupted over geologically short periods. The ocean covered much more of the planet's surface than it does today. Some estimates suggest that 80 to 90% of the early Archean Earth's surface was covered by ocean, compared to 70% today. The ocean was not as deep as the modern ocean, because the deep ocean trenches that exist today, the Mariana Trench and its counterparts, require the specific geometry of modern plate tectonics to form. But the ocean was more extensive. The early Archean Ocean received a continuous rain of hydrothermal material from the abundant mid-ocean ridges and submarine volcanic centers. This material, hot, mineral-rich, mixed with the cooler ocean water, and contributed to the ocean's chemistry. The high rate of hydrothermal activity meant that the ocean was continuously exchanging material with the Earth's interior, a process that maintains certain aspects of ocean chemistry in a state very different from the modern ocean. In this ocean, hot, iron-rich, anoxic, under a sky that was probably hazy with methane and CO2, illuminated by a sun somewhat dimmer than today, the first life was diversifying. From the initial proto-life systems at the hydrothermal vents, whatever they were, life had expanded into the wider ocean. The earliest life forms were likely thermophilic, heat-loving anaerobic microbes that used hydrogen, methane, and other reduced gases as energy sources. These are the organisms most similar to what we find at the base of the evolutionary tree of life, as determined by genomic analysis of modern organisms. From these beginnings, life diversified into what the tree of life shows us as two primary domains of prokaryotes, the bacteria and the archaea, and ultimately gave rise to the eukarya, the domain to which every complex, nucleated cell organism belongs, including all plants, all animals, all fungi, all protists. The ocean was the medium through which this diversification occurred. Life spread through the ocean, evolving in response to the varying conditions of different ocean environments, different depths, different distances from hydrothermal vents, different chemical conditions, and in doing so, producing the incredible diversity of metabolic strategies that characterizes the living world. And the ocean was being changed by this diversification. Every organism that lives in the ocean, by extracting materials from the ocean and incorporating them into its body, and then releasing those materials back when it dies, alters the ocean's chemistry. The accumulated effects of billions of organisms over billions of years are enormous. The ocean's carbon chemistry has been shaped by biological carbon fixation and respiration. The ocean's nitrogen chemistry has been shaped by nitrogen-fixing bacteria. The ocean's sulfur chemistry has been shaped by sulfate-reducing bacteria and sulfur-oxidizing bacteria. The ocean's iron chemistry has been shaped by iron-reducing and iron-oxidizing bacteria. Life and the ocean are not separate systems. They are a single integrated system with continuous feedback between the biological and chemical components. The ocean made life possible. Life made the ocean what it is. Neither can be understood without the other. Part 17. The ocean as mirror. The ocean holds a mirror to time. Not in a poetic sense, though it is poetic, but in a literal chemical sense. The composition of the ocean at any given moment in Earth's history is a function of the inputs and outputs to the ocean over the preceding millions of years. The geology of what was being eroded and dissolved by rain and rivers. The chemistry of what was being erupted from volcanoes. The biology of what was growing and dying and sinking to the seafloor. The climate, which controlled the rates of all of these processes. And conversely, the sediments that have accumulated on the ocean floor are a record of what the ocean contained. Each layer of sediment, each millimeter of accumulated material, represents thousands to millions of years of ocean chemistry. The chemical composition of that sediment, analyzed carefully by geochemists, can be decoded to reveal what the ocean was like when that sediment was deposited. This is the fundamental basis of paleoceanography, the science of the ancient ocean. Cores drilled from the ocean floor, pulled up in long cylinders of sediment that represent millions of years of accumulation, are analyzed layer by layer to reconstruct the history of ocean temperature, chemistry, biology, and circulation. Through this work, we know that the ocean has been warm and tropical from pole to pole during the great greenhouse intervals of Earth's history, the Cretaceous period, 65 to 145 million years ago, when dinosaurs roamed the continents and shallow, warm seas covered what are now the interiors of North America and Europe. We know that the ocean has been cold and ice-fringed during the great glacial intervals, most recently during the ice ages of the Pleistocene that ended approximately 12,000 years ago. We know that the chemistry of the ocean has swung dramatically between states over Earth's history, from times when it was rich in oxygen to times when the deep ocean was anoxic, from times of high salinity to times of lower salinity, from times of high CO2 and warm temperatures to times of low CO2 and cool temperatures. The ocean is not static. It has never been static. But through all of its changes, through all of the billions of years of shifting chemistry and temperature and biology, certain things have remained constant. The ocean has always contained liquid water. It has always been connected to the atmosphere through evaporation and precipitation. It has always been in contact with the solid earth through the exchange of materials at the seafloor. It has always been stirred by wind and heated by the sun and cooled by the escape of heat to space. These constants, water, atmosphere, solid earth, energy from the sun, are the basic parameters of the ocean system. They have been present since the first permanent ocean formed. They will be present until the ocean evaporates, as it will eventually, when the sun becomes a red giant billions of years from now. The specific chemistry of the ocean, the particular mixture of ions and molecules and dissolved gases and living organisms that characterizes our present ocean, is a historical accident. It is the result of the particular sequence of events that happen to occur on this particular planet. On a different planet, one with slightly different chemistry, slightly different geology, slightly different biology, slightly different distance from its star, the ocean, if there was one, would have different chemistry. But the basic role of the ocean, as the medium in which life operates, as the regulator of climate, as the reservoir of the elements cycling through the Earth system, that role is likely a universal feature of planets with liquid water. And the story of how that role was established, the story of the first billion years of Earth's ocean, is a story about how a world becomes a world in which life is possible. Part 18. The faint echo of the beginning. There are places on the modern Earth where you can catch a glimpse of the early ocean. Not directly, the early ocean itself is gone. Its water recycled through the hydrological cycle countless times over billions of years. Its chemistry transformed beyond recognition by billions of years of geological and biological processing. But there are environments on the modern Earth that preserve aspects of the early ocean that operate under conditions similar to those that prevailed billions of years ago. And in these environments, we can see something of what the world was like before oxygen, before complex life, before the ocean became the ocean we know. The hydrothermal vents of the deep ocean are one such environment. The black smokers and the white smokers venting their hot, mineral-rich, sulfur-rich fluids into the cold, deep-sea water, hosting communities of chemosynthetic life that has never seen the sunday. These vent communities are not living fossils in any precise sense. They have 4 billion years of evolution behind them, as much as any other organism, but they are living in conditions that are broadly similar to the conditions of the early ocean. Hot, mineral-rich, chemically reduced, dark. In these environments, we can watch chemosynthesis operating. We can observe the chemistry of iron sulfide minerals catalyzing reactions. We can see the basic metabolic strategies that may have been used by the first life. The anoxic basins of the modern ocean are another. In certain places, the Black Sea, the Cariaco Basin, parts of the Gulf of Mexico, the oxygen minimum zones of several ocean basins, the deep water is depleted in or completely devoid of oxygen. In these places, anaerobic organisms, sulfate-reducing bacteria, methane-producing archaea, sulfur-oxidizing bacteria dominate. The chemistry of these environments resembles, in broad outline, the chemistry of the early anoxic ocean. By studying the microbial communities of these modern anoxic basins, we can learn something about the organisms that populated the early ocean. The alkaline lakes of certain volcanic regions, Mono Lake in California, Lake Magadi in Kenya, have water chemistry that, in some respects, resembles proposed conditions at certain types of hydrothermal vents. These environments host surprising diversity of life. organisms that have evolved to exploit the specific chemistry of these unusual places. None of these environments is the early ocean, but they are windows. They are places where, if you look carefully and with knowledge, you can see the physics and chemistry and biology of a world that no longer exists in its original form, operating in modified, reduced, localized ways. And they are reminders that the diversity of environments in which life can exist is far greater than we might assume from our experience of the surface world. Life did not require the specific conditions of the modern Earth to begin. It required only liquid water, chemical energy, and the raw materials of carbon-based biochemistry. The early ocean provided all of these, in abundance, for hundreds of millions of years before life emerged. The early ocean was patient. Part 19. The ocean and everything that came after. If you were to stand on the surface of the early Earth 4 billion years ago and look around, you would see nothing that you recognized. Not the landscape, which would be black volcanic rock, jagged and fresh, without the weathering that gives modern landscapes their softer contours. Not the sky, which would be hazy and orange-tinted with a composition of gases that would kill you before you had a chance to look at it. Not the sun, which would be slightly smaller and paler than the sun we know, emitting its light through an atmosphere that scattered and absorbed it differently. Not the ocean, which would be a murky, iron-stained, featureless expanse of chemically alien water, lapping against volcanic shores, without any of the biological diversity that makes the modern ocean the teeming, complex ecosystem it is. And there would be silence. Not the silence of a quiet room, where you can still hear the small sounds of your body and the faint background noise of the world. A deeper silence. The silence of a world without anything alive to make sounds. Without insects, or birds, or wind through leaves, or the songs of whales or the crashes of whale-sized predators hunting in the shallow water. Without anything, anywhere, that could process the vibrations of the ocean and experience them as anything at all. It would be the quietest place that has ever existed on this planet. The early ocean is the origin of everything that came after. Not just the origin of the biology that eventually produced complex life, but the origin of the chemistry and physics that make the Earth habitable. The oxygen in the atmosphere produced by photosynthetic life in the ocean. The ozone layer that protects the surface from ultraviolet radiation produced from that oxygen. The stable climate that has allowed complex life to evolve, maintained in large part by the ocean's enormous heat capacity and its role in the global carbon cycle. The biodiversity of the modern ocean descended from the first life that emerged in the ancient hydrothermal vents. The continents themselves, shaped and sculpted over billions of years by the action of water. Everything you can see from the surface of the modern Earth, the mountains, the forests, the blue sky, the white clouds, the green fields, the depth of the night sky reflected in the dark water of a calm ocean, all of it traces back, in some way, to the early ocean. To the first water that accumulated on the first cooling basalt, to the first chemistry that organized itself in the first hydrothermal vent, to the first rain that stayed. And now consider the water in your body. The water moving through your cells, carrying dissolved minerals and molecular signals in the oxygen that keeps you alive, has been on this planet for 4 billion years. It has been part of the early ocean, when the ocean was new and empty and alien. It has been part of the first hydrothermal vent systems. It has been part of the ocean during the Great Oxidation Event, when oxygen began to transform the world. It has been part of the ocean during the Cambrian explosion, when complex animal life first appeared. It has been part of the ocean during the mass extinctions that punctuated the history of life. It has been part of the ocean during the ice ages. It has evaporated from the ocean and fallen as rain, and been part of rivers and glaciers and underground aquifers and the cells of every kind of living thing that has ever existed on this planet. And now it is part of you. This is not a metaphor. It is not a poetic way of expressing a feeling of connection to nature. It is the literal chemistry of what water does on a planet with a hydrological cycle. The specific water molecules in your body tonight have a history that spans the entirety of Earth's existence. They have been witnesses, inanimate, unconscious witnesses, but witnesses nonetheless to everything that has happened on this planet. The water in you is the ocean's memory. Part 20. What? The darkness holds somewhere at the bottom of the Pacific Ocean. Right now, there is a hydrothermal vent. It is approximately 4 kilometers below the surface. The water pressure at that depth is 400 atmospheres, 400 times the pressure of the air you are breathing. The temperature of the water immediately around the vent is several hundred degrees Celsius. The water is black with particles of precipitated iron sulfide. The surrounding ocean, just a few meters away from the vent, is close to freezing, and around the vent there is life. Not the complex, oxygen-breathing life of the surface ocean. Not fish or squid or plankton, but tube worms and clams and mats of bacteria, living in a world of complete darkness, powered by the chemical energy of the vent. Organisms that have never seen the sun and would be destroyed by the concentrations of oxygen that the air above the ocean contains. Organisms that are, in their metabolic strategies and their relationship to their environment, closer to the first life that emerged in the early ocean than to the aerobic, sunlight-dependent life of the surface world. These organisms are not remnants of the past. They are living things, fully evolved, occupying their ecological niche in the modern ocean. But they are connected to the past in a way that most life is not. They are living in conditions that are broadly similar to the conditions in which life began, and they are using metabolic strategies that are similar to those of the earliest life. In them, if you know how to look, you can see an echo of the beginning. The early ocean is gone. The specific chemical conditions of 4 billion years ago cannot be reconstructed. The first life, whatever it was, has not survived in its original form. But the principles on which the early ocean operated water as the medium, chemical gradients as the energy source, mineral surfaces as the catalysts, the slow accumulation of complexity from simple beginnings, those principles are still operating right now in the hydrothermal systems of the modern ocean. The deep ocean is a place where deep time is still present, where the chemistry of the early Earth, modified and overlaid by billions of years of geological and biological processing, can still be glimpsed in the organisms that have found ways to live in conditions that most modern life cannot tolerate. It is a dark place, and a cold place, and a place under pressure that would kill you in seconds. But it is also, in its way, a sacred place, a place where the beginning of the ocean's story can still be felt in the chemistry and the biology of the present moment. Part 21. The ocean and the question of meaning. The early ocean did not know it was building toward anything. It is important to say this plainly. The ocean is a physical system, governed by the laws of chemistry and physics, without consciousness or intention or direction. The processes that produce the ocean, the outgassing of volatiles from the cooling magma, the delivery of water by asteroids, the condensation of atmospheric water vapor were purely mechanical. They happened because the physics of a cooling planet in the habitable zone of a sun-like star makes them happen. The processes that produced life in the ocean, the generation of chemical gradients at hydrothermal vents, the concentration of organic molecules in mineral pores, the slow accumulation of complexity through billions of chemical reactions were also purely mechanical. There was no design. There was no intention. There was only chemistry, operating under the constraints imposed by physics in the conditions provided by the early ocean. And yet here we are, the descendants, at 4 billion years remove, of those first chemical systems in those first hydrothermal vents, complex enough to think about our own origins, curious enough to want to understand them, moved somehow by the contemplation of the vastness of time and the improbability of existence. That movement, that sense of wonder, that feeling of connection to something larger is also a product of the early ocean. Not the ocean's intention, but the ocean's consequence. 4 billion years of chemistry and evolution, operating without direction but also without limit, produced, among an enormous number of other things, the capacity for wonder. The early ocean did not know it was doing this, but it did it. And that seems, tonight, lying in the dark, with the ancient water moving through your body, to be enough. Part 22. What you are made of. Let us be very specific about this, in the way that science is specific about things. Your body is approximately 60% water by weight. That water, the H2O that comprises the majority of you, has been in the ocean. Most of it was in the ocean relatively recently. In geological terms, a few hundred years ago, a few thousand years ago, part of the vast reservoir of the modern ocean cycling through the atmosphere and the land and back to the sea. But some of it has been in the ocean much longer. Water molecules are not labeled with their history. There is no way to tell, by looking at a water molecule, how many times it has been through the hydrological cycle, or what living things it has been part of, or how long ago it was in the deep ocean versus the shallow ocean versus a glacier versus an underground aquifer. The water in you is a mixture of molecules with many different histories, drawn from the entire reservoir of Earth's water. But, statistically, given the age of the ocean and the rate at which water molecules cycle through the hydrological system, it is essentially certain that the water in your body includes molecules that were in the early ocean, that were part of the anoxic, iron-stained ocean of 4 billion years ago, that were present when the first cell divided, that have been through every ocean on Earth, and every glacier, and every river, and every cloud. The hydrogen in your water, the specific protons that are the nuclei of the hydrogen atoms, was forged in the Big Bang, nearly 14 billion years ago. Those protons have been part of the universe since almost the beginning of the universe. They were part of the molecular cloud from which the solar system formed. They were part of the asteroids that delivered water to the early Earth. They were part of the first rain. They were part of the early ocean. And now they are part of you. You are, in a precise and literal sense, made of the universe's oldest material. The hydrogen in your water is as old as matter. The oxygen is the product of a star that exploded billions of years ago. The carbon in your body was forged in the fusion reactions of multiple generations of stars. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, all of these were forged in stellar interiors and distributed through space by stellar explosions, gathered by gravity into a new solar system, incorporated into a planet, and cycled through billions of years of geological and biological processes before arriving in you. You are not separate from the universe. You are a temporary arrangement of the universe's materials, organized by billions of years of chemistry and biology into a form complex enough to contemplate its own origins. The early ocean is part of your history, not as metaphor, as chemistry. Part 23. The long return the water in the ocean is not eternal. The ocean is old, 4 billion years old, but it is not permanent. The processes that built the ocean are also, slowly, dismantling it. At the subduction zones of the modern ocean, the places where oceanic crust is forced back down into the mantle, water is being carried with it. The oceanic crust is hydrated, soaked through with water that has reacted with the basalt of the seafloor, incorporated into new minerals in a process called serpentinization. When this hydrated crust is subducted, pushed down into the mantle, the water it contains is taken with it. Some of that water is released as the subducting slab heats up and the hydrous minerals become unstable. Released water rises into the overlying mantle, lowering its melting point and causing it to melt. The resulting magma rises and erupts as the volcanic chains that run parallel to subduction zones, the volcanoes of the Pacific Ring of Fire, the Cascades of the Pacific Northwest, the volcanoes of Central America, and the Andes. This is one of the primary mechanisms by which water is recycled back to the surface from the mantle. Water goes down with the subducting slab, is released at depth, rises in magma, and is erupted back to the surface as volcanic steam. But not all the water is released. Some of it goes deeper, carried with the slab into the deeper mantle. Some of it is incorporated into the minerals of the mantle transition zone, into the ringwoodite that holds water in its crystal structure at those depths. And some of it may go deeper still, into the lower mantle, where even more exotic, high-pressure phases of water-bearing minerals may exist. Over billions of years, this process is slowly changing the balance of water between the surface and the interior. Water is being carried into the mantle faster than it is being released by volcanism. The ocean is, very slowly, being consumed by the planet. This process is not a threat on any timescale that matters to us. The rate of water loss to the mantle is estimated at roughly a few cubic kilometers per year, a tiny fraction of the ocean's volume of approximately 1.335 billion cubic kilometers. At this rate, the ocean would be substantially depleted only on timescales of billions of years. But the geological record shows that the early Earth had more water at the surface than the modern Earth does. The early ocean covered more of the planet's surface. The volume of the ocean has been decreasing over geological time, very slowly, as the subducting slabs have carried water into the mantle faster than volcanism has returned it. Eventually, in the very distant future, the ocean will be substantially smaller than it is today. And eventually further still, when the sun becomes a red giant and the surface of the Earth is heated to temperatures at which the atmospheric escape of water vapor becomes significant, the ocean may be lost entirely. The hydrogen will be stripped away by the solar wind. The oxygen will react with the surface rocks. The Earth will become dry. But this is billions of years away. For now, the ocean is here. The same water that fell on the cooling basalt of the Hadean Earth is still cycling through the oceans and the atmosphere and the rivers and the ice and the cells of living things. The same water that was part of the first ocean is part of the ocean tonight, is part of you tonight. The long return has not yet come. The quality of ancient dark somewhere in the dark, beneath kilometers of water and rock, in a place that no sunlight has ever reached, and no human being has ever stood. There is something alive. It is not large. It is not impressive in any way that would register to our senses if we were somehow able to observe it. It is a microbe, a single cell, encased in a membrane, processing chemical reactions in the dark, using the energy of those reactions to maintain its own organization against the constant tendency of the universe toward disorder. It does not know what it is. It does not know that it is alive, or that the concept of being alive exists. It has no experience of the world around it in any sense that we would recognize as experience. It has no awareness of the age of the ocean it lives in, no understanding of the 4 billion years of history that preceded it, no conception of the extraordinary chain of events that led from the first rain on the cooling basalt of the Hadean Earth to this particular moment in this particular part of the deep ocean floor. It simply is, simply processing, simply maintaining itself. And it has been doing this, it and its ancestors, in an unbroken chain of cellular continuity for longer than we can fully comprehend. The first cell that divided in an ancient hydrothermal vent, whatever it was, is the ancestor of this microbe. Through 4 billion years of cell divisions, each cell giving rise to daughter cells that inherited the chemical machinery of their parent, each generation slightly different from the last, as random errors in the copying of chemical information accumulated and were selected for or against by the conditions of the environment, the lineage is continued. The lineage has never broken, not through the impact events of the late heavy bombardment, not through the Great Oxidation Event, which may have been the most catastrophic environmental change in the history of life, not through the 5 mass extinctions that are recorded in the fossil record of the last 540 million years, each of which eliminated large fractions of the species alive at the time, not through the ice ages, not through anything that the Earth has done to the surface of the planet in 4 billion years. Life has never stopped. It has changed enormously and continuously. It is diversified into millions of species, occupying every environment that offers any source of chemical energy and liquid water. It has transformed the chemistry of the ocean and the atmosphere. It has built the continents, in a sense, by producing the organic carbon that makes the sediments that the tectonic processes eventually incorporate into continental rock. It has colored the sky blue. But it has never stopped. The thread of life, the continuity of cellular organization, the passing of chemical information from parent cell to daughter cell, generation after generation has been running continuously since it began, somewhere in the ocean, 4 billion years ago. And you are part of it. Not metaphorically, you are a biological organism, and your cells are the descendants, through an unbroken lineage of 4 billion years, of the first cells. The chemical machinery in your cells, the ribosomes that translate genetic information into proteins, the ATP synthase that captures chemical energy, the lipid bilayer that forms the boundary of the cell, these are ancient. They are older than any fossil. They are older than any rock that has survived on the surface of the earth. They have been refined and modified over billions of years of evolution, but they trace back, in their fundamental architecture, to the first cellular life in the early ocean. The water in you is the ocean's memory. The chemistry in your cells is life's memory. You are both at once. And so we come, at last, to the end of this particular journey, though the journey itself, the story of the ocean and life, has no end, only a present moment that keeps moving forward. You have traveled, in the course of this night, from the formation of the solar system to the first rain on the first cooling basalt, from the early magma ocean to the first hydrothermal vent, from the first chemistry to the first biology, from the first ocean to the ocean that is in you right now. You have held, for a few hours, a version of the full span of Earth's oceanic history, not all the details, which would require lifetimes to properly learn, but the arc, the shape of the story. And the shape of the story is this. The ocean is old, and it is patient, and it has been the medium for everything that life has done on this planet for 4 billion years. The ocean did not set out to produce you. The ocean did not set out to produce anything. It simply operated according to the laws of chemistry and physics, in the conditions of a habitable planet, and the consequences of that operation, accumulated over unimaginable spans of time, include you. That is either the most deflating thing you can hear about your own existence, or the most astonishing. Perhaps both. Perhaps it is the nature of deep time that it produces both reactions simultaneously. The ocean before life was empty of biology, but full of the chemistry that would produce biology. It was patient in a way that nothing alive can be patient, patient with the patience of physics, which does not notice the passing of time but simply allows things to take as long as they take. And what it was waiting for, without knowing it was waiting, was the moment when the chemistry organized itself into something that could finally, after 4 billion years, ask the question, what is the ocean? Where does it come from? How old is it? What was it like before we were here? Those questions are you. The ocean built the thing that could ask about the ocean. Let the room be dark now. Let the sounds of the night, whatever they are where you are, wash over you. Let the weight of your body settle into the surface beneath you. The water in you is ancient. The carbon in you is ancient. The space that your body occupies is ancient, the same space that was once part of the early ocean, part of the early atmosphere, part of the early geology of a world just beginning to form. You are temporary, in the way that all living things are temporary. But you are made of things that are not temporary. The atoms in you will persist long after you recycled through other living things, through the ocean, through the rock, through the atmosphere for as long as the planet exists. The early ocean is not gone. It is dispersed. It is in the modern ocean, and in the groundwater, and in the atmosphere, and in the ice at the poles, and in the cells of every living thing on Earth. It is in you. Let it rest tonight. as you rest. Let the ancient dark that surrounds you feel, for a moment, not like absence but like presence, like the presence of 4 billion years of history, quiet and patient, holding you in the same way it has held everything that has ever been alive on this planet. You are the ocean's latest thought, and for tonight, that is enough. Rest now.